Welcome to Manufacturing Lithium-Ion Batteries, a Practical Introduction, Chapter 2, Li-ion Battery Fundamentals. In this chapter, we step away from the noisy factory floor for a moment and go under the hood of the battery itself. Before we worry about mixers, coaters, and formation equipment, we need to understand what is actually happening inside the cell we are building, how it stores energy, what each material does, and why small changes in design can make a big difference in safety and lifetime. Think of this chapter as learning the engine theory before working as a mechanic. The better you understand the fundamentals, the more confident you will be when you are operating, maintaining, or troubleshooting real production lines. So, let us get started with the basics of lithium-ion batteries and build a solid foundation for everything we will see later in the manufacturing process. Learning objectives. On this slide, let me briefly summarize our goal for this chapter. We want to understand what is happening inside a lithium-ion battery during operation, both chemically and electrically. A cell may look like a simple can or pouch, but during charge and discharge, ions, electrons, and heat are all moving. By the end, you should be comfortable with the key processes and with the main state parameters: voltage, current, temperature, state of charge, and state of health. The material follows Chapter 2, Li-ion Battery Fundamentals, in my book Lithium-Ion Battery Manufacturing, which you can use as your main reference for deeper study. The figure on the right shows a model-based battery management system, or BMS, which you can think of as the brain of the pack. It uses mathematical models to estimate how much energy is left, how hot the cells are, whether they are balanced, and whether the pack is operating safely. As we go through the chapter, please keep this picture in mind. The fundamentals we learn here are exactly what the BMS relies on to control a real EV battery safely and reliably. Terminology. On this slide, you see many battery terms. We will not go through every definition here, but I want to highlight one pair that often causes confusion: energy density and power density. You can think of energy density as the size of the fuel tank, how much total energy the battery can store per kilogram. Power density is more like the size of the engine, how fast that stored energy can be delivered. A battery with high energy density can drive the car a long distance, while a battery with high power density can accelerate the car quickly or support fast charging. In real EV design, we always balance these two, like choosing between a marathon runner and a sprinter. Throughout this chapter and the whole program, you will meet many new technical terms like the ones listed here. Do not worry if they do not all stick the first time. Treat this slide as a vocabulary map, come back to it, connect the words to the processes on the production line, and gradually make these terms part of your own battery language. The more fluent you become, the easier it will be to understand problems on the factory floor and communicate clearly with your colleagues. Watt-hour, kilowatt-hour, and the Tesla Model 3. On this slide, we focus on what battery capacity really means. A watt-hour, or WH, is a unit of energy. 1 kilowatt-hour is simply 1000 WH. You can think of kilowatt-hour as the size of the fuel tank in an EV. The higher the kilowatt-hour, the more energy the car can store and the farther it can potentially drive. For the Tesla Model 3 long range, the battery pack is about 75 kilowatt-hours, kilowatt-hour. If the car typically uses around 250 Wh per mile, we can estimate the driving range by dividing 75,000 Wh by 250 Wh/mile, which is about 300 miles. So, from just two numbers, pack capacity in kilowatt-hour and energy use in Wh per mile, you can quickly understand and compare the real, usable energy stored in different EV battery packs. US EV battery manufacturing, capacity and scale in GWH. On this slide, we step up from kilowatt-hour for a single car to GWH, gigawatt-hours, which is how we measure the size of a factory. 1 gigawatt-hour is 1 million kilowatt-hours. The higher the GWH number, the more energy the plant can ship out every year, which means more EVs on the road. Let us focus on Blue Oval SK in Kentucky. Its planned capacity is about 86 GWh per year. If we use our earlier example of a 75 kilowatt-hour battery pack, that is roughly 1.1 million EVs worth of batteries every year. So, this one site alone is designed to supply batteries for more than 1 million vehicles annually. For comparison, the Tesla/Panasonic Gigafactory in Nevada is around 41 GWh, or about half the Kentucky plan, and the combined GM Ultium plants in Ohio and Tennessee have recently moved ahead of Nevada. Other large projects include Stellantis, Samsung SDI in Indiana at about 57 GWh, and LG Energy Solution in Arizona at about 36 GWh. So when you hear someone say, this is a 60 or 80 GWh plant, I want you to immediately picture how many millions of kilowatt-hour that is, and how many EV packs that factory is capable of producing each year. Redox reaction in a lithium-ion battery. On this slide, I would like to connect basic chemistry to what actually happens in a lithium-ion cell. A battery is driven by a redox reaction. Some atoms lose electrons, we call that oxidation, and other atoms gain electrons, reduction. The image on the left is just a generic redox picture. One species gives up electrons, the other one accepts them. In a typical lithium cobalt dioxide, graphite cell, during discharge, the graphite anode is oxidized, by following the following chemical reaction, Li6C6 plus Li plus E. Those electrons flow through the external circuit to the load, while the Li ions move through the electrolyte. At the same time, the cathode is reduced by CoO2 plus Li plus E Li CoO2. If we write the full cell reaction, it is Li C6 plus CoO2 C6 plus Li CoO2, and the arrow to the right means discharging, to the left means charging. The middle image shows discharging. Electrons go from the anode through the load, ions go through the separator, and we get useful power. The right figure shows charging. An external power source pushes the electrons and Li ions back in the opposite direction, rebuilding the original chemical states. If you remember just one thing from this slide, it is this: a lithium-ion battery is simply a carefully controlled redox seesaw that we can drive one way to get energy out, and the other way to store energy back in. Key components. On this slide, let us zoom in and see what a lithium-ion cell is actually made of. You can think of the cell as a layered sandwich. Every layer has a clear job, and changing the recipe of any layer changes the taste of the whole battery sandwich. First, the anode on the right in the image is usually graphite, sometimes silicon blended. Its layered carbon structure is like a parking garage where lithium ions can slide in and out. How well this parking structure is designed strongly affects capacity and cycle life. On the left we have the cathode, materials such as LCO, LFP, NMC, and so on. This is the high-energy side of the sandwich. Cathode chemistry is the main driver for energy density, cost, and safety, so when you hear NMC cell or LFP cell, people are really labeling the cathode. Between them is the electrolyte, a lithium salt dissolved in organic solvent or, in some designs, a gel or solid. It does not conduct electrons, it only lets lithium ions move. That ion highway is critical for efficiency and low-temperature performance. The thin metal foils attached to both electrodes are the current collectors, aluminum for the cathode, copper for the anode. They are like the bus bars of the cell, gathering electrons and sending them to the outside circuit. Finally, the separator is a porous plastic film sitting between the electrodes. It must block electrical contact but still allow ions to pass. Its porosity, thickness, and shutdown behavior are key for safety. As you work in manufacturing, you will be handling and inspecting these layers every day, so it is important to be clear on who does what inside the cell. Lithium-ion battery chemistry. On this slide, I want to give you a big picture view of what is happening chemically inside the cell. At the heart of a lithium-ion battery is a redox reaction, oxidation and reduction happening at the same time. Oxidation means a material loses electrons and becomes more positive, reduction means it gains electrons and becomes more negative. One side of the cell is being oxidized, the other side is being reduced, and that electron traffic is what we harvest as electric power. During discharge, when the battery is feeding a motor or a light, lithium ions leave the anode, travel through the electrolyte and separator, and insert into the cathode. The released electrons go through the external circuit to do useful work on the load. During charge, we simply drive this process in reverse with an external power source. Electrons are pushed back, lithium ions move from cathode to anode, and the cell is restored to its charged state. In the next few slides we will slow this down and look at each step in more detail. Lithium-ion battery chemistry, redox reaction. On this slide, we zoom in on the basic chemistry that makes a lithium-ion battery work, a reversible oxidation, reduction, or redox reaction. During operation, lithium ions shuttle back and forth between the anode and the cathode. They move through the electrolyte and separator, while the electrons cannot go through the electrolyte, so they are forced to travel through the external circuit. That electron flow in the outside wire is the electrical power we use during discharge, and the power we supply during charging. In a redox reaction, one side is oxidized, it loses electrons and becomes more positive, and the other side is reduced, it gains electrons and becomes more negative. In a typical cell the anode is graphite, and the cathode might be lithium cobalt oxide. The electrolyte's job is to let Li ions move between these two hosts, but to block electrons, so that ions take the inside path and electrons take the outside path. You can see the electrochemical equations listed on the right. We will not derive them line by line here, but I encourage you to read them together with this picture. Every term in the equation corresponds to lithium ions leaving or entering an electrode and electrons moving through the external circuit. When you can look at the formula and immediately imagine the ions and electrons moving, you are reading the chemistry the way a battery engineer does. Lithium-ion battery chemistry, discharging. On this slide, we focus on what happens while the battery is in use, during discharge. Think of the cell as a small power plant. Lithium ions leave the anode, the negative electrode, usually graphite, and travel through the electrolyte and separator toward the cathode. At the same time, the electrons that used to sit with those lithium atoms cannot pass through the electrolyte, so they are pushed out into the external circuit, through the load, and then back into the cathode. That electron flow in the outside wire is the usable electrical power for your motor, inverter, or any device we connect. Chemically, the anode is being oxidized, lithium in graphite gives up electrons and becomes Li, which moves into the electrolyte. The cathode is being reduced, it receives those Li ions from the electrolyte and the electrons coming through the circuit, and stores them in its crystal structure. The reactions written on the slide describe exactly this exchange of ions and electrons. I would like you to read those equations later and trace them together with the arrows in the diagrams. Every Li term corresponds to ion motion inside the cell, and every E corresponds to current flowing through the external circuit. If you can connect the formula with this picture, you are really understanding what discharging means in a lithium-ion battery. Lithium-ion battery chemistry, charging. Now we flip the movie and look at what happens during charging. When you plug the pack into a charger, an external power source forces the redox reaction to run in reverse. Lithium ions move from the cathode back to the anode through the electrolyte and separator, and the same number of Li ions that left during discharge must return during charge. At the cathode, lithium is being pushed out of the active material into the electrolyte. You can think of the charger as pulling Li ions out and sending their electrons into the external circuit. At the anode, those Li ions and electrons meet again and are stored in the graphite layers. That is how the battery reloads its chemical fuel. The diagrams show this as a kind of rocking chair motion. Li ions rock from right to left when we charge, and from left to right when we discharge. On the slide, you also see the charge side half reactions and the overall reaction. I would like you to read them later and connect each Li term with the green ion arrows, and each E with the current flowing through the charger circuit. If you can tie the picture, the ion motion, and the equations together, you have a solid understanding of what charging a lithium-ion battery really means. Discharging, inside battery. On this slide, we zoom in and watch what is happening inside the cell while it is discharging. At the anode, lithium that was stored in the graphite starts to leave its parking spots. The Li ions move out into the electrolyte and the electrons are released into the external circuit. That oxidation step is summarized by the first equation on the left. At the cathode, those Li ions arrive and combine with electrons coming back through the load, building lithium, cobalt oxide. That is the reduction step in the second equation. Look at the battery images on the right from top to bottom. They represent the state of the cell over time as the car keeps driving. The red bubbles are Li ions, and the yellow circles above the battery are electrons flowing through the circuit. At the start of discharge, the anode side is full of lithium and the cathode has relatively little. As time goes on, more and more Li ions and electrons pile up on the cathode side, while the anode gradually empties. The charge meter on the left drops as the chemical, fuel, is consumed. I would like you to connect this picture with the overall reaction at the bottom, read it from left to right for discharging and relate each term to lithium leaving graphite, lithium entering the cathode, and electrons flowing through the external circuit. If you can see the ions and electrons moving in your head, the equations will start to feel much more intuitive. Charging, inside battery. Now we look at the opposite movie, what happens inside the cell during charging. When we plug the vehicle into a charger, an external power source forces lithium ions to leave the cathode and travel back to the anode. On the pictures to the right, the red Li bubbles start on the cathode side and gradually move across the separator toward the anode, while the yellow circles above the battery show electrons being pushed through the external circuit in the opposite direction of discharge. As time passes, more and more Li ions and electrons arrive at the graphite anode and are stored there again, they repark in the graphite structure. You can see the charge meter climbing as the anode fills up and the cathode is depleted of lithium. This is exactly the reverse pattern you saw on the previous discharging, inside battery slide. The equations on the left describe this reverse process: oxidation at the cathode, reduction at the anode, and the overall redox reaction. I encourage you to read those equations from left to right as charging and connect each term with what you see in the animation, lithium leaving or entering each electrode and electrons flowing through the circuit. If you can mentally link ions, electrons, and equations, the whole charging mechanism becomes much easier to remember. Charge and discharge rates or C rate. On this slide we talk about C rate, which is simply a way to express how fast we charge or discharge compared to the battery's capacity. If a cell has a capacity of 1 Ah, then 1 C means 1 amp for 1 hour, 0.5 C means 0.5 amp for 2 hours, 2 C means 2 amps for 30 minutes, and so on. For an EV pack you might have, say, 75 Ah modules. A 1 C discharge would be 75 A, a 3 C acceleration pulse would be 225 A. So C rate is just current divided by capacity. Now, how do we read the graphs? The top left graph shows cell voltage versus discharge time for different C rates. The 1 C curve drops fastest, high current empties the battery quickly and pulls the voltage down more. Lower C rates, like 0.2 C, give a longer discharge time and a slightly higher voltage, a gentler, more efficient use of the cell. The top right graph is the remaining capacity versus cycle life for a given charge/discharge pattern. As cycles increase, capacity slowly fades. Notice how the line at a higher temperature falls much faster. When you combine high C rate, 1.5 C charge, 2.5 C discharge, with high temperature, the battery ages quickly. The bottom graph puts it together, cycle life versus temperature for different charge C rates. There is a sweet spot in the middle, around room temperature, where cycle life is highest. Higher C rates, 2C, 3C, always give fewer cycles, and if you also go too hot or too cold, life drops sharply. So, the message for your future work in the plant is, high C rate and high temperature are like driving a car flat out in first gear, you get power, but you pay for it with extra stress and shorter life. Energy density. On this slide, energy density, we focus on how much electrical energy a battery can store per weight or per volume, usually in Wh/kg or Wh/L. In simple terms, it tells you how big the fuel tank is for a given size and mass. In a smartphone or an EV, space and weight are limited, so higher energy density means longer use time or longer driving range without making the device bigger or heavier. Look at the first chart on the right. The horizontal axis is volumetric energy density, Wh/L, and the vertical axis is gravimetric energy density, Wh/kg. Each colored bubble is a different battery chemistry. You can see lead acid is down in the low left corner, heavy and bulky for the energy it stores. Li-ion is up in the top right, it stores more energy in less space and weight, which is why it dominates EVs and portable devices. The second graph at the bottom breaks Li-ion energy density down by components and shows today versus future projection. The total bar is around 200 to 300 Wh/kg now, with a target of roughly double that over the next decade. Notice that most of the improvement must come from better active materials in the cathode and anode, while other parts like the separator and current collectors are overhead that we try to minimize. Power density. On this slide, power density, we are talking about how quickly a battery can deliver energy, per weight or volume, in units like W/kg or W/L. If energy density tells you how big the fuel tank is, power density tells you how hard you can step on the accelerator without the battery complaining. Power tools, hybrids, and EVs during fast acceleration all need high power density. For an EV, we actually need both, high energy density, for long driving range, and high power density, for strong acceleration and safe regenerative braking. A pack with great energy density but poor power density would be like a car with a huge fuel tank but a very weak engine. Look at the graph on the right. The horizontal axis is volumetric energy density, Wh/L, further to the right means more range in a given volume. The vertical axis represents power density, higher up means the battery can deliver higher current and power bursts. Lead acid sits low and to the left, low energy, low power. Nickel, cadmium and nickel metal hydride move up and right, some improvement in both. The lithium families are grouped in the upper right region, they offer both high energy and high power. Within that, you see different Li-ion formats, cylindrical, prismatic, pouch, occupying slightly different spots depending on whether they are optimized more for range or for power. When you work in a factory, the cell design and materials you produce will decide where on this map your product sits, more range type Li-ion, more power type, or a compromise in between. Battery management systems. On this slide, battery management systems, we move from chemistry to the brain that keeps the pack safe. A BMS is an electronic control system that constantly watches the battery, it measures current, voltage and temperature from the pack, runs algorithms, and then decides what to allow or what to stop. If you like, the cells are the muscles, and the BMS is the nervous system. In the diagram on the right, you can see those measurements coming in on the left side, current, voltage, temperature, going into the green BMS board. On the right side, the BMS outputs key estimates and commands, state of charge, SOC, how full is the tank. State of health, so, how old or degraded is this pack. Thermal management and power optimization, it talks to cooling systems and the inverter/charger to limit power when things get too hot or too low. Inside the pack, the BMS also performs cell balancing, making sure that no single cell becomes the weak link by charging too high or too low. For you as technicians and engineers, the message is simple, even a perfectly manufactured cell can fail early if the BMS is poor, and a good BMS can greatly extend the safe life of a pack. On this final slide, I want to leave you with some references and further study materials. If you are curious and want to go deeper into how lithium-ion batteries really work, please explore the videos and articles listed here. They cover topics we have touched on in this chapter, basic working principles, detailed animations of charge and discharge, amp-hour and watt-hour calculations, C-rate tutorials, and practical explanations of battery management systems. In addition to these links, remember that your main reference is our textbook Lithium-Ion Battery Manufacturing. I strongly encourage you to read the corresponding sections and, if possible, browse other technical papers or manuals from your own factory. Whenever you have time, pick one link or one reference at a time and connect it back to the slides we have discussed. Treat this slide deck as a roadmap and these resources as optional side quests to strengthen your understanding of lithium-ion batteries and EV packs. This brings us to the end of Chapter 2, Fundamentals of Lithium-Ion Batteries. Thank you for your attention. In the next lecture, Chapter 3, we will continue with lithium-ion battery cell structures and cell types. Thank you. We'll meet again in the next lecture.